Hello.
You talked about gears, like sir,
Yes, sir.
gearbox,
Correct, sir.
inertia.
Oh.
Yeah.
Yeah, gears. After that, we talked about this one
We
also
spoke
final.
about viscous force that
Comparison between all.
Sir, comparison between some table you have shown, sir.
Yeah, that's it. So now that we have seen the mechanical modeling, what is a mechanical model? How to model a mechanical system? Starting with basic components, then we build, say, spring and damper, a subsystem, and a damper, spring and mass, another subsystem, spring mass damper. Then we say how to model hydraulic motors, actuator also. All these things we have seen, correct? We already studied more than 6 to 7 hours, and to know why you need modeling, how model equation can be generated, then how you can do simulation. Simulation will be a matter of higher level, but now we understand it. Next important part of this one, what we are going to see is sensors. Let me share. I have shared, I think so.
That's
Sir,
visible, sir.
Screen visible, sir.
Yeah. Is now visible now?
Yes, sir. Visible, sir. Visible.
Okay. Okay. Now the next important, because I already told you there are 5 sections, main important section. First one is mechanical modeling, and before that the need for mechatronic system, example for mechatronic system, all those things already we saw. Now we are going to see next one, what you call as sensors and actuators for automation. First we start with sensors. Okay. Shall we record once again today? We'll see whether it comes neatly so that.
Yes, sir.
Then what I will do is I'll mute everybody. You will not be able to talk till I this one. Okay. Good evening, student. Today we are going to. Okay, let me record it. We'll see.
Recording in progress.
Good evening, student. Today we are going to see next important chapter of mechatronic course. It is about transducers, sensors, and actuators. First, let us see what is a transducer, what is a sensor, what is the actuator, the definitions. Then we will talk more about the sensors, different type of sensor, how they are working. One that is completed, then we look into the actuators in the next part. First, let us start with the definitions. When we talk about the sensors and actuator, first we need to define what it is. Definition generally says that what the sensor will do or what actuator will do, and with some example. Now, if you see any textbook on sensors or instrumentation, you will come across 3 words. That's what I'm mentioning here. The first one is called as transducer. The second one is called sensor. The third one is actuator. They are all interrelated. First, the definition of transducer is, it is a device which converts one form of the energy into another form. That's what the definition. General definition, we say it is 1 or 2 lines. So the transducer definition is a device which converts one form of energy to another form. Next, the transducer can be a sensor or it can be actuated. This is the second definition. A transducer can be a sensor or an actuator. If it is sensor, what is the definition? If it is a sensor, the definition is a device which provides information or data, or also I can say signal about the physical quantity or environment which it is measuring. Sensor is going to measure some parameter. It can be temperature, force, pressure, or light intensity, humidity, or any other parameter you wanted to measure. I am talking about a sensor used in engineering field. It is going to measure the parameter and provide a electrical signal. That's what we call as a data, which is proportional to the input parameter. For example, if the input parameter is a force transducer, if the force is vary from 0 to 10 Newton, the sensor should produce some electrical signal, maybe 0 to 100 millivolts or 0 to 50 millivolts. So then this device is called as sensor. Again, it should be noted, the sensor also input is pressure. It is a mechanical energy, which is converted to electrical energy, which is called EMF or voltage. So that means sensor also converts the input energy into another form of energy, electrical signal, which can be used for quantifying the input parameter. So it is called sensing, quantifying the input parameter using a device we call as sensing. So sensor also is a transducer. That's why we said transducer can be a sensor or it can be actuated. The example, thermocouple, which converts heat energy into electromotive for EMF. The unit for this is volts. EMF is the electromotive force. Unit for it is voltage. But many times we say the voltage. Voltage is a unit for the electromotive force generated by a battery or a generator or a photo cell or any device which generates electricity. It actually generates electromotive force only. That is the correct technical name. What is unit for electromotive force is volts. So we always say voltage. Voltage and current we say, that is well understood. It's nothing but a EMF. Next thing is, what is the definition of actuator? Actuator is a device which does some work. That means mechanical work, actuation is going to do some work by converting one form of the energy into another form. Basically, the input energy can be electrical voltage or a chemical energy. In case of IC engine or a jet engine, we are feeding fuel. Fuel called chemical. That when it is burned, the chemical energy is converted to heat energy, which in turn generates the torque or force, moving the piston or rotating the turbine or the gas turbine, which is going to provide the thrust or the torque to the wheels, correct? Thrust in the aircrafts, jet engine. In case of IC engine, we are talking torque to the wheels. So the device converts the one form of energy, chemical energy, into a mechanical energy. Or in case of take electric motor, you are supplying voltage and current. That means the power you are electrical power you are supplying or electrical energy, which is converted into mechanical energy. There may torque and speed. So that's why the example for the actuator is an electric motor in which electrical energy is converted into mechanical torque and speed. So this is the definition for transducer, sensor, and actuator. Next, in this slide, we are going to talk about what we call the electronic sensor. Generally, if you see in books, generally they talk about sensors. Nobody in even textbook, specifically no book mention about electronic sensor. But I generally try to classify modern sensors as electronic sensor. These sensors will measure any physical parameter like temperature, pressure, humidity, force, speed, light intensity, and the sensor generates a proportional electrical signal. So that's why I call this kind of sensors as electronic sensor. A sensing device which converts a physical or mechanical or optical energy to electrical signal is called electronic sensor. You may ask a question, does it mean that do we have or had mechanical sensors? Yes, we had mechanical sensors for measuring pressure. For example, Bourdon tube. Other one is a bellows, flexible bellows, which can be used for measuring pressure, which was used for a very long time before the invention of electronic sensors. Even now, those sensors are in use in industries, in old equipment, all those things. But modern equipments are using electronic sensor, which the output is always the electrical signal. which is proportional to input parameter. That's why I call it electronic sensor. Next, the sensor can be a bidirectional sensor. The example is piezoelectric sensor or ultrasound sensor. Generally, for example, if you take a thermocouple, I'm just showing you thermocouple, typical thermocouple. It is made of two metal wires. I say the chromal and aluminum, or copper constantine, Cu and constantine. These are the two dissimilar metal. These are wires made out of this one, and they are fused to form a junction. This we call as a junction. It can be anything. There are different types of thermocouple there. Now, if the junction is subjected with some temperature, okay, it is subjected with some heat flux, correct? Heat flux or heat energy, then it produces a heat. Temperature is there because of heat energy. Temperature is there at this junction. When temperature is provided junction, this produces an EMF, electromotive force. Mostly, it will be in the order of millivolts or microvolts per unit degree temperature. For example, input temperature vary from 0 to 1 degree. For example, this temperature, chromal aluminum, can maybe produce 0.1 millivolt or 0.01 millivolt. That means 10 microvolts. That is what they produce. Most of the sensor, especially the thermocouples, which can measure the even minus 100 to, for example, to plus 1200 degree temperature can be measured with the platinum rhodium temperature thermocouples. Those thermocouples can withstand those temperature, and when the input is varied from this, we can see that the range, we are going to see the range of input is going to be minus 100 to plus 1200, that means 1300 degree centigrade is the range of the input sensor, for which it may produce maybe 0 to 100 millivolts. The exact number you can see in the data book. I'm just for understanding, I'm just saying, you can see that the output is not even volts, it is in the millivolts only. Per degree, if you see, it will be microvolts. Now, these sensors are called a unidirectional sensor. What it takes, I am giving heat energy. Output is an EMF, electromotive force. As I told, electrical signal, which is proportional to heat at temperature. Temperature varies from 0 to 1000 degree. It may produce 0 to 80 millivolts. Or another one, 0 to 400 degree. The copper constant, it may give 0 to 400 degree input. Then it may produce 0 to 50 millivolts as output, proportional. So these sensors are called unidirectional. Input is given, output is an electrical signal. But in case of the bidirectional sensor, for example, take a piezoelectric sensor. If I take a piezoelectric crystal, something like this looks, I say it is a cuboid, having some height, width, and this one. Then it is put on the hard surface. And if you apply a force vertically, I am applying a force vertically in the direction, I call this a Z direction. This direction I call it a Z. And then if I put electrical conductors, this surface 90 degree, because there are two surfaces, you can see the totally 6 faces. If I measure across this, it produces an electrical charge. This is piezoelectric crystal. Piezoelectric crystal, if I take, which is in cuboid shape, if I apply in this direction, it produces electrical charge across this direction. This one. So this charge is proportional to the force applied. Charge is proportional to force applied. So, for example, if I talk, this can be used for measuring pressure also. In IC engine, in cylinder pressure measurement. For that, we are using piezoelectric pressure transducer. For example, because I have used extensively, for example, Chrysler. Chrysler is one company, Mr. Chrysler in Switzerland, or AVL from Austria. These two companies are very famous company which make the pressure sensors, piezoelectric pressure sensor, which can be used for IC engine. Wherever you want to measure pressure, you can use it. And the pressure sensor available, pressure which can measure 0 to 10 bar or 0 to 1 bar, very low pressure also, or 0 to even 500 bar or 1000 bar, high range also available. You can select whichever range. When you this one, they produce a proportional charge in terms of picocoulomb. There is a picocoulomb. If I remember correctly, per bar pressure, 1 bar pressure, if you apply the crystal in-cylinder pressure sensor, it produces mostly 10 picocoulombs per this one. That means if the sensor is 250 bar pressure, it can measure means 0 to 250, it will produce 0 to 2500 picocoulombs of charge. Okay, so this sensor, now this piezoelectric sensor or in case of ultrasonic sensor, already told you, if you apply a pressure vertically, it produces a charge in this direction, Q. Okay, instead of that, so that means input is force, output is electric charge. In this case, it can be used as a sensor. It is used as a sensor. Okay, instead of that, what we can do is, if I apply electric field or electrical voltage, okay, I apply a voltage. For example, say 100 volts or 50 volts, whatever may be. I apply voltage across this phase, but I'm not applying force. I'm just directly applying just electrical voltage alone. Here, what will happen is the crystal deforms, the height changes. Correct? Initially, the height was, for example, 10 mm. Each side is 10 mm, 10 mm, 10 mm. Correct? Height, width, and breadth. Now when I apply 0 volt, this one. 10 mm was the height. Now I apply, say for example, 100 volts. Then what will happen? The height will increase. The crystal deforms and physically it become bigger. Now it is, for example, 11 mm. Correct? In one direction, vertical direction, it becomes bigger. So we call it a strain. Correct? There's a strain is produced, it deforms. Now, if I remove the voltage, again it come back to 10 mm. So if I apply a pulses, voltage pulses, which is varying from 0 volts to 100 volts, pulses like this, what will happen? The crystal height, which was a 10 mm, it will increase and come back. Increase and come back. Please, this is 10 mm original, now 11 mm. So the height increases. So I can use this crystal as a small actuator, micro actuator, to move something. If I wanted to move some items in micrometer, millimeter accuracy, I can use piezoelectric crystal as an actuator. Because what is an actuator? I give input voltage, input energy as an electrical voltage and current V and I. Because of that, there is a mechanical force is created. Correct? Physical, it generates a force in this direction. Force is created. So that means piezoelectric crystal can be used for measuring force, pressure, or torque, or you can you make it as a actuator. So this kind of sensor transducers are called as bidirectional. This one sensor, because it can be used for as a sensor as well as the actuator. So even ultrasonic sensor also same. Ultrasonic sound sensor, if you apply electrical voltage, it will generate, vibrate and generate sound signal. Only thing is the frequency is above 20 kilohertz. Right? It is above greater than 20 kilohertz the frequency. 20 to 50 kilohertz generally range for this one. We know that 0 to 20 kilohertz is the audible range for humans. So since the frequency is above the human hearing capacity, we call as ultrasonic. So the range can be maybe 50 kilohertz also. Even it can be 100, but general range is 20 to 50 kilohertz is the ultrasound sensor. Okay, this crystal, ultrasound crystal also, if you apply electrical voltage as square pulses, and it will generate sound waves at the same frequency. This is 1 kilohertz sound electrical signal apply, it will generate 1 kilohertz sound wave. So crystal vibrates because applied voltage. Instead of that, if I hit the, for example, I have the ultrasound crystal, something like this, again QMAT, and the sound waves comes. This is my sound wave, ultrasound waves coming from some other crystal, and it will generate a voltage. It will generate a voltage, proportional millivolts output. So in this case, this now it is a sensor. If I ultrasonic sound hits the crystal, it generates a proportional millivolts. Instead of that, if I apply a voltage, it will vibrate and produce sound. So these two the transducer, piezoelectric called as bidirectional sensor, because they can be used as a sensor and actuator. Another important thing which we have to notice in case of electronic sensor is the sensing device always extracts or absorbs some energy to produce the signal. So we know that if we take about thermocouple, I take my thermocouple. It is a 2-wire DC will have a junction. It is subjected to physical contact with an other object. Which one where you want to measure the temperature? Maybe let me start with another. I have a surface, a metal surface, and this is surface, and this is heated. Correct? I am giving heat energy Q. So automatically the temperature of this cube, metal cube, increases. Now I want to measure the temperature of this metal cube. What I will do is I use thermocouple. Thermocouple junction will be made to touch the surface. If it touches, what will happen? The heat will be transferred from the surface. This location I am showing some other color. For example, the temperature of 50 degree. Correct? The metal cube, which is a solid cube, is heated by supplying heat energy. Currently pressure is temperature 50 degrees is maintained. Now I want to measure temperature. That means the TC, thermocouple, is touching. Once it touches, before touching, thermocouple junction temperature or room temperature, for example 30 degree. When it touches, what happens? The heat in this area will be transferred to the thermocouple, because the metal, the junction looks like a small bulb. It absorbs some amount of Q. Delta amount of Q is taken from the object, or whose temperature we are measuring. That object temperature was originally 50, and thermocouple temperature 30 degree. When you touch it, what will happen? The heat from the surface will be transferred to thermocouple. Once heat is transferred, what will happen? This temperature will come down. It will not be 50, it may become 48 degree, depending on how much heat energy was taken. So now, because of that, the thermocouple generates some electrical signal. This electrical signal, what we are measuring, is not proportional to original 50 degree. It is to 48 degree only, because what is measuring is lesser temperature, because thermocouple itself has taken some heat. For otherwise, if without heat transfer, thermocouple will not produce electrical signal, because the depending on heat energy supplied to thermocouple junction only, it produces the sensing signal. That means if I touch any surface, whose temperature thermocouple measuring, the thermocouple absorbs some energy. That means extracts some amount of energy. So the temperature automatically reduces from 50 degree become 48 degree. We'll say that this is called as loading effect. That means the sensor absorbs some energy because of the measured parameters, not the actual parameter, because the measured parameter is a temperature. Now temperature reduced because we have taken some heat. So this is called as loading effect. That means if I want to design a sensor, next statement says good sensors are designed such that the loading effect is minimal. They should not absorb energy from the source which it is measuring the parameter. That is very important for designing this one. Then next thing is the output is always electrical signal. We know that the input parameter, force, temperature, or humidity, whatever it may be, the electronic sensor produces proportional electrical signal, but the electrical signal consists of additional noise. The signal should be only proportional to input. For example, I take my force transducer. My input is given to 0 to 10 Newton force we are applying. This is output. This is my input. Output from my force transducer is always millivolts, 0 to, for example, 100 millivolts. That's what it has to suppose produce. As you increase the force, 1 Newton, 2 Newton, 3, 4 something, the output also is coming. Now if I plot that and I connect it, I get a graph. Okay. But the graph should be something like this. If my temperature linear increasing, the output also linear increase should be a straight line with the run. But actually, if you see in the way post transfer output using oscilloscope, if you try to measure the signal what is coming, correct? So if for example, my input force is 10 Newton, I applied a force at now I am measuring the output signal. The output signal should be in the order of I'm putting in the same graph I am showing. It is millivolt, but not as same scaling. But understand that this is also considered 100 millivolts and 10 Newton, 0 to 10. So my signal should come something like this. Instead of that, it will come something like this. 100 millivolts plus or minus some oscillation will be there. This is called as noise. This noise is called a EMI, electromagnetic interference. Who is generating the, for example, cell phones? Your cell phones are generating TV signals and spark plugs, DC motor, brushes, all the wherever the voltage arcing is there, or the voltage varies. For example, electromagnetic waves generated by cell phone, TV, radar, all these things. They are called, including stars. Sometimes the stars also generate electrical pulses, which is called a cosmic radiation, and it can generate electromagnetic waves also, noise. Those things will be picked by my sensor, correct? Sensor can pick those noise. So that means the original signal also is a flat curve which is there, but above that, this is the noise. So both are added together. The signal coming out sensor has the electrical voltage proportional to input and also the noise. So noise should be removed. For that, we need to use filters. That's what we are going to see next chapter, talking about electronic amplifiers and filters. Now, the signal, another thing is noise, not only noise, I told you, the sensor generally produce voltage in terms of millivolts. 0 to 100 millivolts thermocouple for 0 to 1000 degree, or force transducer. I said 0 to 10 Newton, the output is 0 to 100 millivolts only. This is what the force transducer will produce. So that means these signal need to be amplified. So for that, we'll be using electronic amplifier, and to remove the noise, we'll be using filter. Now, modern world with the advent of lot of technologies like VLSI technology, MEMS technology, right? These technologies helps in developing a compact sensor. That means generally, as I told you the previous statement also, if I have a thermocouple, the thermocouple is this is my junction. It is subjected to Q because of that is heat. Because of that temperature, the temperature will be, because of temperature, there will be heat will be absorbed by junction. It generates EMF, which is in the millivolts. This signal, since it is on 0 to say 100 millivolts something, and it needs to be amplified. So what I'll do, I connect a electronic amplifier. It will be connected to electronic amplifier. From there, it will be connected to filter, electronic filter. Now, 0 to 100 millivolts, which is proportional 0 to 400 degrees centigrade, is amplified to, for example, 0 to 5 volts. That means 5000 millivolts by the amplifier. After that, and still it has the noise. This noise is there. So it will be given to electronic filter. It will remove the noise. Once that is done, it will be given to the measuring device. Measuring device, which are a display and what you call ADC, analog to digital converter, and microprocessor or microcontroller with display. Modern or digital electronic, with that will have display where the measured quantity is displayed to the end user. So that means we need amplifier, we need filter. So now, some 50 years before, even now, many of times you have sensors separate. This from the sensor, the signal is taken through small wires and connected to amplifier. From the amplifier, again wire will be there. It will connect to our filter circuit. From there, it goes to measuring unit. All these things will be put in a small unit, correct? Measuring maybe a few inches inside, right? That means measuring device. Except the sensor, the whole thing will be put inside one box, right? A metallic box or plastic box having some dimensions, some weight. But nowadays, because of MEMS and VLSI technology, all these things put together. What is the sensor, correct? Under the amplifier, filters, and ADC, DS, all these things are put in one IC, integrated circuit. We call it IC. Only what you need is the output display and power supply. Power supply and the output display. Measuring the output display will be additional this one. All other things will be put in a single IC. Okay. So what is the advantage? It has a lot of advantage. One thing is it become very compact and less weight, dark by less volume, and it is highly rugged, reliable, and also the EMI noise can be substantially reduced when I have the what you call a smart sensor. Smart sensor means it has amplifier, filter, and also microprocessors, all those things. So that signal is processed, finally it is displayed. Okay, so those kind of sensors are called as the smart sensors. Okay, now we'll see the classification of electronic sensor. I told you in here, I said, what is an electronic sensor? It measures any physical parameter, generates proportional electrical signal. Okay, it should have the following. It can be a regular sensor, unidirectional or bidirectional, and it should have less loading effect. That means it should not extract energy from which it is measuring the quantity, and in that case, the measured quantity will be very close to actual this one. So loading effect should be avoided by designing the sensor. The sensor designer should consider all those things. Loading a minimal. Then we need to have the signal conditioner like amplifier and filter so that the sensor signal properly amplified, remove noise, and convert into a quantity which can be shown on the display. It can be an analog meter or this one. So now modern sensor we call a smart sensor, which integrates everything: sensor, amplifier, and noise filter, ADC, and also the microprocessor. It is a small computer, everything put on a single IC. Inside a single semiconductor chip, like IC, it is a single unit. We call it a MEMS sensor. Nowadays, we call it as MEMS sensor, which is also called as smart sensor. Also called as smart sensor. Now, when we talk about the sensor classification, we can see that the electronic sensor can be further classified. Please note that you are not going to see in any book specifically. Don't come and say that, so we have not seen specifically which talks of electronic sensor. This is what I generally, since I'm teaching this course for a long time, I used to coin this word electronic sensor, because the input can be any parameter, output always electrical signal, which can be given to amplifier directly. That's right. So again, when we talk about classification of sensors, the sensor can be classified as a broad category depending upon how it senses the input parameter. Again, this classification also generally may not see in one book. Since I am teaching this course for a long time, I classify like this for better understanding for the students. One is the sensor resistance itself changes. For example, you have a sensor for a strain gauge, and normally when there is no force is applied or no pressure is applied on sensor, the sensor has some resistance. It is basically strain gauge, nothing but an electrical wire. We are going to see in the today or tomorrow. We are going to see that the strain gauge is nothing but an electrical wire. When it is subject to force or pressure or torque, is physically dimension changes. The length increases, the area reduces, so automatically resistance changes. So if the sensor resistance changes due to the input parameter and the change in resistance is proportional to input parameter, those kind of sensor is called as change in resistance type sensor. Example is the strain gauge and resistant temperature, which is also called RTD. And if you take a strain gauge, the resistance strain gauge changes based on this formula, where resistant of strain gauge, I can RS, substitute SS, that strain gauge, SJ, I can say, is nothing but rho into L. This is a small L, not I. Length rho L by A, where rho is called resistivity of the material, which using which the strain gauge is made. Generally, strain gauge are made of metallic metals, or sometimes they use semiconductor also. Mostly it is the metal. So rho is called resistivity of the metal of which the strain gauge is made. L is called the length of the strain gauge wire. A is the cross sectional area of this wire. So this is the now if you apply a force, if I, for example, I have a wire. This is my wire, and it has length, for example, 100 mm. 100 mm length, and because wires generally it is a cylindrical shape, solid, say for copper wire, aluminum, whatever it may be. Like this stained gauge wire also, it can be cylindrical or it can be square type or rectangular type. I am talking cross sectional area, and I say that the cross sectional area is, for example, 2 mm square, and length is 100 mm. Okay, so this is my L, this is my A, this wire length, and this is my A cross sectional wire. And for example, it made of for copper. Understanding, but generally it's not made of copper. Some other special material, and the company generally they keep it as a secret, but there are composition generally you can find out. So for example, we call resistivity. Resistive rho is, for example, 0.015, something like that. That will be generated that value. Now, I know 2 is the 2 mm square, 100 mm length, and the rest of this one, I can calculate resistance of the strain gauge RSG equal to this 100 multiplied by resistivity 0.0015 divided by area. Area, we know that 2 mm. Right? Appropriate, then you will find out this is the resistance. Now, if I apply a force onto the strain gauge and it stretches, I apply, for example, force equal to 5 Newton. What will happen? The wire, because of this one, I have one side it is connected, correct? It cannot move, fixed, correct? This end is fixed. This side I'm applying a force of 5 Newton. What will happen? The wire length will increase from the 100 mm, it become 105 mm. My L become 105. My area will become not 2 mm, mm square. It may be become 1.85 mm square. But rho is going to be same. Material we are not change. It is going to be 0.0015. Now again, if we call my RSG, after applying the force, you will have different value. Correct? Definitely it will be more than the value what you have got it. Okay. So for example, this equal to 1 ohm something it comes exactly. This may be 1.1 ohm. Okay. I'm just saying can be a new value. This is how the strain gauge works. The next one is RTD. RTD works using this principle. In this formula, R is the resistance of RTD. There is a resistant temperature detector. This sensor can be used for measuring temperature. This is used for measuring force, strain gauge, correct? Torque, or can be a pressure also. These all parameters can be used in strain gauge. RTD used for measurement temperature measurement. Temperature can be measured using this one, similar to thermocouple. It is made of many times it can be made of copper with some composition or platinum or Cu plus some material. I don't remember exactly, and many times they use platinum wire. So it is nothing but again a platinum wire which may be made as a coil, and if the platinum wire at, for example, at 30 degree, given platinum wire is resistant 100 ohms. Now, if the platinum wire is immersed with the water or touches a hot surface, okay, whose temperature is at, I said 30 degree centigrade, and now it is subjected to say 100 degree boiling water. Now the resistance may become 1 or 2 ohms. From 30, the platinum wire, which is called as RTD, resistant temperature detector, is subjected to higher temperature, lower temperature. Automatically, the resistance changes. The resistance changes. So this property is used for measuring temperature. How the temperature and resistance are connected is this formula. R is the temperature at any given temperature. Right now, I took my RTD sensor, plunge it inside a hot water. That temperature, this is what? This is the temperature of what I am measuring. This is 100 degree. And in this formula, R equal to R naught into 1 plus, this is called alpha, not A. You can note that this is called alpha. They are called temperature coefficient of this one. Alpha is called as temperature coefficient of material. Each material has its own coefficient that you can find out from the data sheets. Copper has something, aluminum, platinum, like that. Every material has a value. If you know that, then you can calculate what are the resistance using the formula. Where R naught is called the RTD sensor resistance at T naught. T naught is called reference result. T naught is called as reference temperature, and R naught is called as reference resistance. Okay. For example, I say 30 degrees centigrade is my reference temperature. That time, my R naught, the RTD sensor was 100 ohms, for example. Okay. Now, the T is the current temperature which I am trying to measure. For example, this is 50, and this is already we know 30. And alpha also we know temperature coefficient alpha equal to, for platinum is 0.00025 something. I don't know the exact number. Generally, it will be like this only. Very small value. Then you can substitute here. Already we know 30. We don't know the 50 correct temperature. We don't know, but we know we can measure this resistance. But if I know the temperature, I can find out what is the resistance. Okay. So now, because I wanted to measure T, which is unknown, I can rearrange the equation T equal to, in terms of R naught R and T naught and alpha. Then I can find out what is the temperature. If resistance is known at the current temperature, I can find the current. This is how the RTD works. Okay. The next type of sensor called change in its capacitance. The sensor capacitance is we know the resistance is a fundamental property of the electrical parameter, one of the property of material. Other one is capacitance. Capacitance can be formed using two conducting plates. We are going to see that. And if the capacitance of the capacitor changes due to the measuring parameter, then the type of sensor is called the sensor whose capacitance changes. Capacity type sensor I will call this as capacity type or capacitance type. I can say the capacitance type sensor. Okay. So generally, if I have two conducting plates separated, the formula, how it works is basically, this is a governing formula, C equal to A into epsilon divided by D, where A is called as the common area between two conducting plates. We'll see in the coming slides when we talk about this. And D is the distance between two conducting plates. Epsilon is called the permittivity. Epsilon is called permittivity of the dielectric media which separate two conducting plates. Basically, generally the capacitor will be shown like this. This is, I say, P1 on metallic plate having some area, cross-sectional area. I have another plate, same shape, and this one. This I call it a P2. And between there's a gap. This is a D, separated by D. Okay. And the area of this one's A, capital A. And then the in between the gap, I can insert a dielectric material. Okay. I can say that dielectric material having some thickness is inserted. The thickness will I calculate. For example, this is equal to 1 mm. D equal to 1 mm. And the area of the conducting plates, if you look A, I say A equal to 100 mm square area. Okay. Then in between the dielectric material having thickness is there, is permittivity equal to, for example, 2. Correct? We call it relative permittivity. Then I can say the capacitance C equal to A is 100 mm square multiplied by epsilon equal to 2 divided by D. So, and appropriate unit if you use it, correct, SI unit, all these things should be millimeter or meter, centimeter. And then we say so many farads. The capacitance of this capacitor is nothing but two parallel conducting plates separated by a distance D, and in between there's a non-conducting. Dielectric means non-conducting material. Correct? Non-conducting material have dielectric, which have permittivity. Then I can calculate this one. Now in this equation, by changing any of this, right, A or D or epsilon, I can change the capacitance. Okay, I can change the capacitance. So that means this kind of sensors are used for measure angle measurement and displacement. Linear displacement, angular displacement can be measured using this. Then the third type of is called a change in inductance. And this is called inductive type sensors, which is used for measuring the RPM, inductive RPM sensor or LVDT, which is called as linear voltage differential transformer. Linear voltage differential transformer. Short form is LVDT. Both this is used for measurement, displacement measurement, and the inductive sensors are used for measuring, can be used for measuring displacement or like speed, there are rotating object speed or velocity. All this thing can be measured using inductive sensor. We'll see that. Basic formula behind this one is, if it is inductive type sensor, then the voltage generated in the inductor is nothing but a coil made of conducting wire, and inside that, for example, I have a coil, and inside that I have a magnet, a permanent magnet, which is called a core. Core, it has north and south pole. This is my coil. Coil has n number of turns. Now, because of since the magnet is there, there will be a magnetic field from like this. It has phi. Okay. Now, if I change the magnetic flux by varying the voltage, correct? Because magnetic will have only when there's a current flow, is like the electromagnet. There's a current, and that is proportional voltage. And if I change the current voltage, there's a current changes. That means the magnetic flux produced by the sensor will change. That is one thing. Instead of that, what I'm doing is, if instead of applying voltage, they call electromagnet. Instead of that, what I did is, now in this case, already I have a magnet. Correct? I don't need an electromagnet. This is the principle of governing the generator. Correct? In generator, there's a magnetic flux which changes when the magnet is rotated. It induces voltage. But in case of inductive sensor, already I have a magnet, so there's a magnetic flux, and the voltage there has to be a voltage produced here, EMF produced in the coil, that is proportional to this. Okay, this is the third type of sensor. The fourth type is called piezoelectric sensor. Piezoelectric sensor, already when we talked about bidirectional, already told you, if you apply mechanical force or pressure, it generates electrical charge. The charge is proportional to the amount of the force applied. Right? When you vary 0 to 100 bar, 100 Newton force, or 0 to 100 bar pressure, or 0 to 100 Newton meter torque on a piezoelectric crystal, and then it produces a charge which is proportional to this one. This kind of is called piezoelectric sensors. They are used for measuring pressure, knock, engine knock, and accelerometer. correct? Acceleration measurement. The next one is thermoelectric effect. Thermocouples, we know that it works on what you call Seebeck effect. This is the person who invented this one. That's what I told you. If two dissimilar metals are taken, Cu copper constant wires, and form a junction, if it is subjected to temperature, the heat energy, then it produces a EMF. This is called as Seebeck effect. This sensor can be used for measuring temperature. That works on based on thermoelectric effect. We will see it later when we talk about sensors. The last one is photoelectric sensor. Photoelectric sensor uses a photodiode or phototransistor or LDR. These sensors produce proportional electrical voltage depending on how much light is hitting the sensor. Right? When light hits a photodiode or a phototransistor or LDR, the current flowing through the device changes. The change in current is proportional to light intensity. That means using this photodiode or phototransistor light dependent resistor, we can measure light intensity. If you see any of these sensors anywhere in any machine, those sensors will fall in one of this category. Change in resistor type, change in capacitance, or change in inductance, or piezoelectric effect, or thermoelectric effect, or photoelectric effect. Any type of sensors will, more 99% of sensors with the electronic sensor fall under this category. I stop here. I think next faculty will be waiting. Tomorrow we'll continue about sensors. Okay. Thank you very much. See you tomorrow.
Thank you, sir.
Okay.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah.
Recording stopped.
Give your attendance chat message before leaving.